back. So continuation on the ZhongHua paper. I'm now going to go on to section B, okay, or paper 2, section B. So this is the question. It's a question on moments. And so this is the setup. I've got a plank, 2 forces, and this is the pivot. So state the principle of moments. Principle of moments, you have to remember as a definition. So you have to remember this. I've already kind of pre-written it. You have to remember it and write it exactly as how I have written it. So I'm not gonna read through it. You can read it yourself. So this one is just memory work, yeah? Next, they want you to calculate the net moment and its direction acting on a plank. Okay, you may assume that the plank has negligible mass. All right, so the net moment, so I have got, let's calculate my anti-clockwise moment first. So this will create an anti-clockwise moment, okay? So my anti-clockwise moment, I have to take F times the perpendicular distance, all right? So the F, the force is 10 Newton, and I have to multiply the perpendicular distance, which is 0.5 meters. So this will give me 5 Newton meter. Okay, sorry for the interruption. Again, it was just finished downloading on the previous video. Okay, so where was I? Yes, calculating the anti-clockwise moment, and now I've got to calculate my clockwise moment. And the clockwise moment is due to this fella here. Okay, same thing. I have to take a force multiplied by its perpendicular distance to the pivot. This time the force is 2 Newton, and the distance to the pivot is 1 meter. So this will give me 2 Newton meter. Okay. And therefore, my net moment is taking my anti-clockwise moment, which is 5 Newton meter. I take away my clockwise moment, which is 2 Newton meter, and I'll end up with 3 Newton meter. So my answer is 3 Newton meter, and anti-clockwise moments wins. Therefore, the direction of the net moment is in an anti-clockwise direction. Okay, so this is part A. Let's go on to part B now. Okay, so this is one of those toys where it kind of goes back to its original position no matter how you hit it. So they already labeled that this is the CG. Okay, so it's halfway between the two side masses and directly underneath the pointy bit. So this is now in its off position. Yeah. So they want me to mark X where the CG is. Now the CG has not changed. Yeah. So let me try and draw this as accurately as I can. Hopefully this is going to work here, and then it's going to be down here. So the CG is somewhere here. I'm going to mark it with an X and label it CG. So the CG has not changed position. It was here, it still is here. Okay. So now describe and explain the motion of the toy when it is released. Okay, so the CG, let me explain it first in my words. The CG is where all the mass, where all the weight of the object acts, right? So I'm going to draw this force called the weight, and weight is always perpendicularly downwards. So this fella is going to create an anti-clockwise moment, and this is the pivot. So therefore, this fella is going to rotate in an anti-clockwise moment back to its starting position because the weight is going to create an anti-clockwise moment about this pivot. Okay. All right. So first, let's describe the toy will rotate anti-clockwise back to its starting position. And why this is so? Because as the weight the line of action of the weight from the CG creates an anti-clockwise moment about the pivot. Okay, pivot being this point here. Yeah. Okay, so now the next part says that there is a defective toy. Yeah, so after releasing it, it remains in this position. So very simply, if it remains in this position, means the line of action from the CG of the weight is in line with the pivot point here. That's why things remain in equilibrium, because the CG is in line of the pivot point. So the very simplest position where you can mark the center of gravity is just here. Yeah, let's put a dot here and we mark it as Y. Now, of course, you can mark it anywhere along this line. It is going to work, but like I said, the easiest is just here. Okay, and explain why the position of center of gravity causes the toy to remain in this position after it is released. Okay, so at position Y, the CG does not, or maybe I shouldn't say the CG, the line of action, due to the weight of the toy does not create a net moment. Yeah, so because the CG is over here, there is no clockwise or anti-clockwise moment to rotate this fella back either left or right. Yeah. So very important, you have to understand the theory of CG and its position and how that creates a moment if it's over here because it is not in line with the pivot point, or if it's in line with the pivot point, what happens? Can? So some keywords that you have to take note of when you're answering questions like this, you have to use line of action, moment in this case, yeah, and over here, you always have to talk about the moment that will bring the toy or whatever object that the question might be asking back to its original position. Okay, don't just say that it turns it back to its original position. Be specific with saying anti-clockwise moment or clockwise moment, things like that. Okay, so these are some keywords that you have to take note of. Yeah, so hopefully you understand this question. If not, email me, tell me what your question is, and I'll try to address it. Yeah. So for now, I will stop the video here, and I'll go through the next question in the next video. Right?